So partial derivatives are the derivatives that we find for functions that have more than one variable. And that's why we say partial derivative. Because when you differentiate a multivariate function, you're trying to juggle two variables. So you need to hold one constant and then differentiate the other variable with respect to the other variable. So for example, we want to differentiate and then evaluate the partial derivatives. At -3, -3. Okay, so if we say that our third variable is z, in other words, z equals fxy, we've got two independent variables and then a dependent variable z, then the way we refer to the partial derivatives is we differentiate z with respect to x. And this is denoted as fx, like that. And then dz, dy, now we're differentiating with respect to y, is denoted fy. This is not a 2, this is a fancy d. I write the d like that to show that I'm finding the partial derivative. Because if I just wrote dz, dx with a normal d, I'm not really signaling to the person that's reading my work that this is, I need to signal that, hey, I'm talking about a multivariate function here. Because sometimes it may not be obvious that it's a multivariate function. But when you have an f here with a little x, that means you're differentiating with respect to x. And if you have an f with a little y, that means you're differentiating with respect to y. So that just means that not x, but y here is treated as a constant. And here, x is treated as a constant. Okay. So I'm differentiating this with respect to x. Y is treated as a constant. So that means if I take the derivative of this, it's going to be 0 because y is treated as a constant. And if I'm differentiating with respect to x, I take 3 times -5, that's -15. And then, of course, I subtract 1 from the 3. And so that is my derivative of f with respect to x. Similarly, if I'm differentiating with respect to y, I hold x constant. So x is treated as a constant, so the derivative of -5x cubed is 0 because this whole thing is treated as a constant. And the derivative of 6y squared is 2 times 6, that gives me 12x. When I subtract, y. When I subtract 1 from the 2, I'm just left with y to the 1. So I get 12y. So that's how you take the derivative for for multivariable functions. And let me do another example. Oh, I forgot to evaluate at -3, -3. So to do that, we just take here, x is -3, y is also -3, and I just plug those in, And negative 3 squared is 9. And multiplying by negative 15 is going to give me negative 135. And then at y equals negative 3, this is going to be Fy is 12 times negative 3, which is negative 36. Okay. Any questions on that? All righty. So this time we have f of xy given to us as negative 8e to the 5x minus 3y. And we want to find the partial derivatives evaluated at 1, 0. So first we're going to find the partial derivative with respect to x. So this is an exponential function, right? And the way we differentiate exponential functions is we just write down what you see. So we have negative 8e to the 5x minus 3y, and then you multiply by the natural log of the base, but the base is e, so the natural log of e is just 1, so we don't have to multiply by 1 because that's not going to change our problem at all. And then the third step, remember, was to multiply by the derivative of the exponent. That's applying the chain rule. So the derivative of this with respect to x means that we hold y constant. The derivative of negative 3y is going to be 0 when you're differentiating with respect to x. And the derivative of 5x is just going to be plain old 5. So my first derivative with respect to x is going to be negative 40 e to the 5x minus 3y. And then at 1, 0, this is negative 40 e to the 5 times 1 minus 3 times 0, which is just negative 40 e to the 5. So that's evaluating this derivative with respect, I'm sorry, at 1, 0. So the partial derivative with respect to x at 1, 0 is negative 40 e to the 5th power. Now doing it for the partial derivative with respect to y. You copy what you see and then multiply by the derivative of the exponent. Now we're differentiating with respect to y. So that means we're holding x constant. The derivative of a constant is 0. So the derivative of 5x is going to be 0. The derivative of negative 3y with respect to y is going to be negative 3. Negative 3 times negative 8 is 24. I'll just go ahead and write the exponent here. And then I note that at 1, 0, this is going to be equal to 24e to the 5 times 1 minus 3 times 0, which is just 24e to the 5. So when I differentiate with respect to a certain variable, you know, whether I differentiate with respect to x, it's going to give me something different if I differentiate with respect to y. So just be understanding it, all because you're holding a different, you know, you're holding one variable constant in one situation and you're doing it, holding the other one constant in the other. So it's going to give you different results when you're differentiating like that. Any questions on that? It's kind of tricky. You're just going to have to practice, and then if you get stuck, you may need to, get in touch with me to help you through some of it, or if you have a tutor. Don't forget the math department has tutors available for you if you need some real, extra help with this. And there's a link in the news items. If you scroll back far enough down in your news items, you'll see a link for a tutor if you need that. Okay, or you can meet with me, however you want to do it. Whoops, that paper's not so. All right. I guess I'll just do some more examples. Let's talk about second order derivatives. That would probably be a good time to do that. And I'm going to revisit this next time on Thursday. So we finished section 6.1, so you can go ahead and start the homework or do the homework for 6.1 if you want to. And you can go ahead and start the homework for 6.2, but I will do some more examples next time if you get stuck. So try to take a look at it, and then you can bring me your questions on Thursday if you had trouble with them. So we talked about the first order partial derivatives. Now we're going to do second order. So remember, with the second order, you're just taking the derivative of the derivative. So with partial derivatives, you have 4 second order partial derivatives, and they are named fxx, fxy, fyx, and fyy. This is what we call them, and what that means is the definition is the derivative with respect to x of fx. This is the derivative with respect to y of fy. And we have the derivative with respect to x of of fy. And then the derivative with respect to y of fy. Okay, so let me just point something out here. This second x here refers to this x there. This y is referring to the fact that you're differentiating with respect to y. Here you're differentiating with respect to x, and here you're differentiating with respect to y. The first letter tells you which function, which of the first partial derivatives are you differentiating. So here, in these two, we're differentiating fx. Here we're differentiating it with respect to x, and here we're differentiating it with respect to y. In these two situations, we're differentiating the partial derivative with respect to y. We're differentiating that with respect to x. So we start with the first derivative and differentiate it with respect to x. Here we're also starting with the first order derivative and differentiating with respect to y. So those are the situations. Let's do an example. And so we have let's see, I better leave that there for now. Let's suppose our function is the polynomial 2x to the 7y minus 3xy plus 5y. Now first you're going to differentiate with respect to x. So that means you're going to hold y constant. So what I'm going to do is I'm going to rewrite this function, and I'm going to move the y's next to the constants just to kind of emphasize the fact that we're holding y constant. So I'm going to write it as 2y x to the 7th minus 3y times x plus 5y. And I'm going to take my marker and my color green and show you that I'm grouping these two together because they're constant. And then I'm going to group those together because they're constant, and then this is constant. Okay? So that means that my fx is going to be 7 times my 2y, and then I'm going to subtract 1 from 7. And then here, this is just a linear, this x has a power of 1, so the derivative, negative 3yx, is just negative 3y, because that's the constant. And the derivative of this is 0, because this is constant. Remember, y is being treated as if it were a constant. So now, simplifying this, I get 14y x to the 6th minus 3y. That's our first order derivative. Okay? Now, let's do the same thing. We're going to find now fy. So this time, x is being treated as a constant. So I'm going to put parentheses around these and treat them as constant. And the derivative with respect to y then, here we just have y to the 1. So the derivative is just going to be 2x to the 7th power minus 3x. And here it's going to be plus 5. Any questions on that? Okay. So now to find the second, these are the first order. Partial derivatives. And we want to find the second order. So we have to differentiate these. We're going to differentiate this with respect to x, and then we're going to do it with respect to y, and then we're going to differentiate this with respect to x, and then we're going to do this with respect to y. And that's how we get 4 different second order partial derivatives. Okay? So let's go ahead and start. I'm taking this, let me put a box around these. These are the ones I'm looking at right now. I'm taking this one, differentiating with respect to x. So y is going to be treated as a constant. So this becomes 6 times 14y. 6 times 14y is 84y. But then I subtract 1 from the 6, that's going to be 5. I'm differentiating with respect to x, so y is constant. So when I take the derivative of this, it's going to be 0. Now I'm going to do the same, use the same function, but I'm going to differentiate with respect to y. So x is treated as a constant. So we have 14x to the 6th times y. So the derivative of that with respect to y is just 14x to the 6th. And here, taking the derivative with respect to y is going to be minus 3. Now I'm differentiating this partial derivative with respect to x. So this tells me which one I'm differentiating with respect to. So this, I'm differentiating with respect to x for this function. And so I take 7 times 2, that's going to be 14x, subtract 1, that's going to be 6. Here the derivative of negative 3x is just negative 3. And then the derivative of 5 is 0. Notice these two are the same. And that's typically what's going to happen. Not always, there are a few exceptions, but generally you're going to have the same function here. And I think it has to do with continuity, but I'm not going to delve into that. Generally, polynomials behave very nicely. And so this being a polynomial, these two are going to be equal. Now I take this second function, which is my partial derivative with respect to y, and then I differentiate it with respect to y again. But notice there are no y's in here. So we treat this whole thing as a constant, as if it were like, say, 27. You just treat the whole thing as a constant. The derivative of a constant is 0.